In this project, the flow behavior passing through a porous medium is simulated. Studying fluid flow in porous media is one of the most widely used fields of science. A porous medium is made up of mostly perforated materials and contains pores and void spaces within itself. Various body tissues, such as the skin, bones, kidneys, and lungs, can be considered as porous medium. Porous media are widely used in a variety of industries, such as food, oil, textiles, building materials, insulation, filters, and membranes. In this project, fluid flow through a porous medium with three different porosities is investigated. The fluid domain consists of an upstream flow domain, a porous medium domain, and a downstream flow domain. The geometry of this project is designed in ANSYS Design Modeler and is meshed in ANSYS meshing. The type of mesh created for this geometry is structured, and the total number of elements are 35,017. In General Setup tab, you will see different dialog box from scale to units. By clicking on Scale dialog box, a new window will appear. In the open window, you may see the domain extents or the maximum value for each coordinate based on your geometry. On the view length unit, you may choose from different units available in this window, from meter, foot, inches. In the scaling part, you are able to change the mesh dimension based on your meshing software geometry you've used. For example, you've used the meter dimensions for your mesh. You can go ahead and change the scaling factors to meters, or you can change it into whatever units you want. For example, you can change it into feet, to inches, and so on. By clicking on the Check dialog box, you will see that in the Console tab, the Fluent software will start to check your mesh and geometry for any errors. By clicking on the Report Quality dialog box, you will see that in the Console tab, the Fluent software will start to check your mesh quality. For example, you will see that the Fluent software will give you the orthogonal quality and as maximum aspect ratio. You may double-click on the Display dialog box and a new window will appear, which gives you the ability to choose between the different parts of your geometry you want to show in the Fluent software. In the Appeared window, you may choose between different parts of your geometry to show or not show just by clicking on them. Also, the type of the solver is defined to be pressure-based, and the velocity formulation is in absolute form. The steady state simulation has been used, and the results are not a function of time. Also, the gravity is not taken into account. By double-clicking on the energy under the Models tab, a new dialog box will appear. In the Appear dialog box, we enable the energy equation since we want to know the temperature distribution along the geometry. The two-equation K-epsilon model with the use of a standard roll function is used in this project for analyzing the turbulent flow since it is robust, economic, and has reasonable accuracy for a wide range of turbulent flows. Our main material for this simulation is counted to be the air. By double-clicking on the air, a new dialog box will appear. In the Open dialog box, we are able to change the settings of our material. For example, in this dialog box, which is related to the air, we can see that the density and the Cp, specific heat, thermal conductivity, viscosity, are shown. Since we are simulating the compressible flow in this project, we need to go ahead and change the density from the constant to ideal gas. After double-clicking on the part porous under the fluid cell zone condition, a new window will appear, enabling us to activate the porous zone option. Under the Porous Zone tab, you will see two direction vectors, direction 1 and direction 2. Now the software automatically sets values for this direction based on your geometry, and you do not need to change any values in this section. In the next section, the values for viscous and inertial resistance are needed. From the theoretical perspective, porous media are modeled by the addition of source term to the standard fluid flow equation, which is composed of two parts, viscous and inertial loss term. In laminar flows, the pressure drop is typically proportional to velocity, and the values for inertial loss term can be set to 0. And of course, at high flow velocities, the value under inertial loss can be viewed as loss coefficient along the flow direction. In the final section, you will see that under the thermal model, equilibrium thermal model is chosen, which means that there isn't any temperature difference between the solid and the fluid flowing inside the porous medium. Under the relative viscosity section, the value for relative viscosity is set to be 1, which means that the fluid viscosity does not change when it flows inside the porous medium. In the open window under the Porous Zone tab, we change the fluid porosity to the value we desire. After clicking on the inlet boundary condition, you will see that the type of the boundary condition is defined as velocity inlet. By clicking on the Edit dialog box, a new window will appear. In the open window in Velocity Magnitude section, we may change the velocity magnitude entering the inlet boundary. After clicking on the absolute boundary condition, you will see that the type of this boundary condition is set to be pressure outlet. Stationary motion and adiabatic condition is defined for all the wall type boundaries. After double-clicking on the method, you will see that a new window will appear showing you different schemes for pressure-velocity coupling, which in this project, the simple scheme is chosen to do the simulation. Now the simple scheme is kind of a segregated solver, in which a relationship between velocity and pressure correction are used to enforce mass conservation and to obtain pressure field. Also, you can see that the spatial discretization methods are shown in this window. For example, the pressure discretization is defined to be second order, or for the momentum, second order upwind. Also, you can change this discretization into other formats, like you can change them into first order upwind. After double clicking on the controls button, a new window will appear showing you different values for and under relaxation factors. We may also change the under relaxation factors. These factors may be between 0 and 1. Based on the simulation and the project we are doing, we may change these under relaxation factors. But remember that the values set in here are the recommended values for the project, and we highly recommend you to not change these values. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the 0, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the new, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well. For example, in this project, a pressure drop report alongside the porous zone is defined, and when the simulation is running, you may see how the pressure drops when the flow passes the porous zone. After double-clicking on the residual button, you will see that a new window will appear, showing you the absolute criteria for the residuals of each equation. For example, you can see the absolute criteria for continuity, x velocity, y velocity, and so on. These criteria refers to the difference between the errors of each iteration, and it refers to the fact that if the error is less than these criteria, those equations have reached convergence. Also, as you can see, the convergence criterion is set to be in absolute form. After clicking on the initialization button, a new window will appear, and you can choose between two methods of initialization, hybrid initialization and standard. In the standard method, you will be able to choose and set the value for different parameters of the flow field based on your idea, or actually you can choose from the compute from drop-down list. These values refers to the values used in the first iteration of the simulation process. You can go ahead and choose the all zones so that the software will automatically calculate the values averaging from all the zones. After double-clicking on the Run Calculation button, you will be able to change the total number of iterations you want your simulation to progress. After defining the number of iterations, by clicking on the Calculate, the simulation will start. In this section, the pressure, velocity, and velocity vector contours are presented to you. In the 3D pressure contour presented to you in this slide, you may see how the pressure drops after passing the porous medium. Just like the 3D pressure contour, you may see the pressure drop here in the 2D pressure contour as well. In the 2D velocity contour, you may see that the velocity value near the walls are equal to 0, which enforces the no slip boundary condition. Now for creating the pressure drop plot, you just have to change the plot direction by changing the Z value to 1. After that, by just clicking on the interior part downstream, porous, and upstream, a plot will appear showing you the pressure drop in these zones. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com.